All right, so this video is going to introduce you to limits. We're going to be talking about limits graphically and then also numerically and how they just kind of all come together as a big concept here. So there are three types of discontinuity that are being demonstrated in this first piece right here. We call this a hole. What is meant by a hole is that there is some factor that factors out of the top and the bottom of the function. So because I have x squared minus 4 in the numerator, I could factor this into x plus 2, x minus 2 on the numerator. My factor of x minus 2 would cancel in the top and the bottom, and so f of x behaves just like the line y equals x plus 2, except it does not have a domain at x equals 2, because if I plug x equals 2 back into this original function, I get something that's undefined. I can't divide something by 0, so I just don't have that part inside my function, so we call that a hole when a factor in the top and the bottom cancels. Another type of discontinuity that we are going to have is going to be a jump. What happens is as you approach, in this case x equals 2, from what we call from the left, moving in towards the right, that is a different value than if you approach 2 from the right and go to the left. So this is a hole discontinuity. This is a jump discontinuity. And then we also have a vertical asymptote as a type of discontinuity. This is the parent function graph of 1 over x squared moved to the right 2. Therefore, I'm going to have a vertical asymptote here at x equals 2. And so let's think about what's going to happen with limits at each one of these parts. So limit means as x gets really, really close to x equals 2, what ends up happening? Well, when we have a hole, you still will have a limit because your outputs are still going to approach a special y value here. Even though there's a hole, we can get ridiculously close to x equals 2, and I see that these values of y are going to get really, really close to 4. However, for this jump discontinuity here at x equals 2, I don't have one y value that I approach. I have two different ones. On this right-hand side, as I approach 2 from the right, I end up having outputs of 1. When I approach 2 from the left, I have outputs of -1. So I don't have a limit with a jump discontinuity because I need to be able to approach one y value. Vertical asymptotes, what that means is if I were to look at the limit as x gets really, really close to a number, in this case x equals 2, my y values go to either plus or minus infinity. So as I approach an x value, in this case x equals 2, if y gets really, really close to plus or minus infinity, or doesn't get really close to, if it approaches plus or minus infinity, then I say a vertical asymptote is going to be there. All right, let's look at how to evaluate something like this first limit if I wanted to use a table of values. So I'm going to plug this in to Desmos as a function. And I'm actually going to go ahead and call this f of x. And I want to get values really, really ridiculously close to f equals 2. Now, if I plug in f of 2, it'll tell me undefined. It does not like that value. So if I want to plug in a number smaller than 2, like 1, I could then create a table of values. So in x equals 1, y equals 3. 1.5 would be another x value really, really close. So 1.5 and then 3. I could do 1.9. I could do 1.99. I could do 1.9999999. And you can see that we actually get to a value that rounds to 4 when I plug in those values. I could also go from the other side. So I could look at 3. I could look at 2.5. I could look at 2.1. I could look at 2.0001. And you can see my y values get really, really close to 4 as x gets really close to 2. Algebraically, which we will do this in another video in more detail, but I already know that this function behaves really, really close to x plus 2. So I could just do what's called substitution or direct substitution and do the algebraic manipulation of this function of f, plug in 2, and you will see 2 plus 2 does give me 4. Again, more on direct substitution in another video. All right, let's continue with looking at a table of values and also looking at the graph here in order for us to find these limits. So as x goes to 4, notice when I plug in 4 here, I have 4 in the denominator. I don't like having 4 in the denominator. And in fact, I end up having a hole. And you can see that here in the graph, that I would have a hole at x equals 4. You can track this over graphically to see that this limit is going to be 0.25 or 1/4. Let's look at a table of values to see why that's going to be true. So in this case, I have the square root of x minus 2 over x minus 4. Let me double check that. Yes. All right, and again, if I plug in f of 4, it won't let me do that. Well, let's think about numbers smaller than 4. So let's think about 3. And then let's look at 3.5. And then let's look at 3.9. And then 3.99 and 3.999. You can see as x here is getting closer and closer and closer to 4, my output values are getting really close to 0.25. I can go from the other side of 4 as well. So we could start at 5. That's a really big jump to the right. But I could also do 4.5, so halfway between 4 and 5. So now I'm approaching 4 from the right or from numbers bigger than 4. And you can see it's 2.4. Well, another step closer to x equals 4 would be 4.1. Another step closer to x equals 4 would be 4.01. Another step even closer would be 4.001. And you can see my numbers here for my y get rounded to 0.25. All right, if I just have a graph like this one and I don't give you a function and I want to know the limit, all you can do is estimate from the graph. So because it looks like as I approach -1, x equals -1, what does my graph do? My y values look like they are getting really, really close to L equals 3. Now notice in this graph, g of -1 is 4. That's that circled dot right there. But that is not the same thing as my limit. My limit is 3. So we would write the limit as x goes to -1 of g of x equals 3. And then take a note that g of -1 equals 4, and that is not the same as 3. So sometimes we'll have piecewise functions where the whole gets covered up, and so then we have a continuous function. In this case, the whole does not get covered up, so we have a discontinuous function. All the domain values are accounted for, but it is not continuous.